Okay, we're going to go over what we did in 10.4 today, which was special patterns. And the first special pattern that we've got is the difference of perfect squares. So as you can see here, there is a formula, and it is very intentionally called the difference of perfect squares. Difference meaning we have a minus in between, so that minus right there is what makes it the difference, and the perfect square part comes in because A and B are numbers and they are perfect squares. So for example, we may have x squared minus 36. Now that is a difference because of the minus. 1x squared is a perfect square and 36 is a perfect square. So the way the difference of perfect squares will always factor is I take the square root of the first number there, which is 1, and put a 1 in each beginning spot of these sets of parentheses. Then I take the square root of x squared, which is x, and I put an x in each set of parentheses. As far as the signs go, 1 will be a positive, 1 will be a negative. The square root of 36 is 6, so I put 1 6 there and 1 6 there. That's one example. Another example, x squared minus 25. Again, I'm understanding that there is a 1 in front of the x, so I put a 1 in each first position, an x, because the square root of x is x, so I put 1 in each. One sign is a plus, one sign is a minus, and the perfect square of 25 is a 5, and I put a 5 in each set of parentheses. Then we get to something a little bit more involved, where we we put a number, a, in front of the x squared, and, let's, I don't want that to factor the GCF. Okay, so 4x squared minus 49. What we have to look for is that this a value is a perfect square. 49 is a perfect square, and the minus in between then tells us that that is the difference of perfect squares. So I will factor this. I have two sets of parentheses. The square root of 4 is 2, so I'll put a 2 in each leading position. The square root of x squared is x, so I'll put one of those in each. One sign is a plus, one sign is a minus, and the square root of 49 is 7. Okay, so that is the basic difference of perfect squares. There may also be an instance here where you've got something like 2x squared minus 242. Now looking at that, 2 is not a perfect square, and neither is 242. However, if you recall from 10.1, where we were factoring the GCF, the greatest common factor, 2 is something that can factor out of both of those terms. 2 divided out of 2x squared leaves me with just x squared. And 2 divided out of 242 leaves me with 121. Okay, so by factoring out the greatest common factor, I can see that what's left inside my parentheses might just be the difference of perfect squares. Understanding that there is a 1 here, 1 is a perfect square, x squared is a perfect square, 121 is a perfect square, and I've got the difference between them. So that is the difference of perfect squares. So I will factor two sets of parentheses, a 1 in each leading position, an x right next to it. 1 is a plus, 1 is a minus. The square root of 121 is 11, so I put an 11 in each parentheses also. But the one thing I have to remember here is to bring down my 2 with it. So 2x squared minus 242, although it may not look like a perfect square, because at this point right here, it's not the difference of perfect squares, but by factoring out the greatest common factor, we do in fact get a difference of perfect squares. So that's something that you will need to recognize. another example of that would be something like 63 x squared minus 175. Now 63 is not a perfect square, but one thing that can come out of each one of those, the greatest common factor that we could pull out of both of those numbers is a 7. Okay, that's the greatest common factor. When I divide 7 out of 63, I get 9 x squared. And when I divide 7 out of 175, I get 25. Now, what's inside my set of parentheses is, in fact, the difference of perfect squares. 9 is a perfect square, x squared is a perfect square, 25 is a perfect square. What's separating them is a minus sign, so it is the difference of perfect squares. Keep in mind that you cannot factor the sum of perfect squares because what you get is an imaginary solution, which is not what we're dealing with here. So I'm going to bring down my 7. I've got 2 sets of parentheses here. The square root of 9 is 3, so I'm going to put a 3 in each position. The square root of x squared is x. I have a plus, I have a minus, and the square root of 25 is 5. So that's as far as the difference of perfect squares go. Now, what I'm going to do is kind of separate the screen here and talk about another pattern, and I want to bring in another kind of a quadratic, which is, so let's look at this one in particular. We have 36x squared plus 12x plus 1. Now, the difference between what I just wrote on the right and what is written, say, over here on the left is, if you notice, I've got 3 terms right there, but I've only got 2 in the other one. This 3-termed thing, polynomial, is called a trinomial, where the other one has only got 2 terms, so that's a binomial. So that's the only difference. But the main thing is that these 2 things do not factor the same way. We cannot use the pattern for the difference of perfect squares over here on the right because I've got a trinomial. The difference of perfect squares only factors binomials. Notice what I'm missing over here is the x term, which I've got over here. So that's what the whole entire difference rests upon, is that I'm missing an x term with my difference of perfect squares, but I have it in the trinomial. So what we do to factor this, Caitlin should know from class that if this second sign right here is a positive, both the signs in my factors will both be the same, and they will both be whatever that sign is right there. So I know that both of these signs are going to be pluses. Now, the way that I know that this factors as a pattern, I'm going to look at the first number, 36. I'm going to look at the last number, 1. If 36 and 1 are both perfect squares, the rule is I will take the square root of 36, which is 6. I will take the square root of 1, which is 1, and multiply them together. Okay? So 6 times 1 gives me 6. If I double that number and I get what the middle term is, which is 12, then I know that this is a trinomial that will factor into 2 perfect squares. So I have 6 is the square root of 36. X is the square root of x squared, and 1 is the square root of 1. And if I were to test myself, per se, by foiling this out, 6x times 6x is 36x squared. Then I have 6x times 1, which is 6x. Then I go to the middle here. Let me change colors. I'm going to go to the middle here. 6x, whoops, kind of overshot it there. There we go. 6x times 1 is another 6x, and 1 times 1 is 1. So if I add all of that together, my like terms are 6x plus 6x, which is 12x plus 1. So again, if you've got a trinomial, a 3-termed polynomial, and the first number is a perfect square, and the last number is a perfect square, you can follow the rule per se. Take the square root of the first number, square root of 36 again is 6. Take the square root of the last number, the square root of 1 is 1. Multiply those together and double it. If that product is equal to my middle term, it will factor into this pattern right here. Okay, so let's do another one of these. X squared plus 14x plus 49. Okay, I have a 1 here. It's understood. I can write it there, but you don't need it. 1 is a perfect square. 49 is a perfect square. So I know so far that my rules are being followed. Take the square root of 1, which is 1. Take the square root of 49, which is 7, and multiply them together. 1 times 7 is 7. If I can double that and get my middle term here, then I know that this will factor using my pattern. And it does, because 7 times 2 is 14. So I'll have 2 sets of parentheses. An x will go in each one, or you could say 1x. Doesn't matter. Both my signs are the same. They're both positive, so I'll have a plus in each one. And then the square root of 49 will go in as 7. So the way that we can rewrite this, we could say x plus 7 times x plus 7. But another way to rewrite this, because if you notice, both these sets of parentheses are identical, you could write 1 x plus 7 and square it. Not necessary, just a different way to note the solution. So we could, let's do another one like that, because this might not always work. So we're going to check that. Okay, so we may have something like x squared minus, 4. I'm sorry, I probably shouldn't do that one because that's kind of not one of the rules that I want to follow here. Let's try this one. This will be better. 4x squared minus 10x plus 25. Okay, so I'm going to start by looking for the perfect squares. The leading term for perfect square. Okay, the constant, 25, perfect square. All right, I'm going to take the square root of 4, which is 2, the square root of 25, which is 5, and multiply them together to get 10. If I double that, I would have to get that middle term. Well, 10 times 2 is 20. Well, negative 10 is not the same thing as 20. So this is an instance in where those rules don't work, and this does not have a particular pattern. Okay, so it won't always work. Now, another thing that we did in class today was factor out or factor very long, drawn out difference of perfect squares. For example, one problem we might have would be, say, 36 x to the 8th, y to the 6th, z to the 4th, minus 25 a to the 2nd, b to the 10th, and c to the 16th. Yikes. Okay, again, we're going to look and see about these perfect squares before we decide that this is a pattern. 36 is a perfect square. 25 is a perfect square. We've got the difference between them. Now we need to look at the variables. If we're dealing with perfect squares, that's based on an index of 2, okay? If you can take your exponents here, your 8, your 6, your 4, your 2, your 10, your 16, all of those are even numbers. As long as your exponents are even numbers, in order to find the square root of them, you just divide the exponent by 2. In other words, if I have x to the 8th, divide 8 by 2, and x to the 4th is the perfect square of x to the 8th. Because I just cut the exponent in half, divided by 2. All right, so we're going to use that to see if this, in fact, is the difference of perfect squares. Everything has to have a perfect square, or the rule of difference of perfect squares does not apply. So 36 is a perfect square. X to the 8th is a perfect square because 8 is an even number. Y to the 6th is a perfect square because 6 is an even number. Z to the 4th is a perfect square because 4 is an even number. Same with the A, the B, and the C. So I know that I've got a difference of perfect squares. I'm going to set up my 2 sets of parentheses and start writing what goes in each one. 36 is a perfect square, so I'll put a 6 in each position. X to the 8th is a perfect square. 8 divided by 2 is 4, so x to the 4th will go right next to the 6. Y to the 6th is a perfect square. 6 divided by 2 is 3. So y cubed will go next to the x to the 4th. Z to the 4th is a perfect square. 4 divided by 2 is 2. So I've got z squared. Now it looks like I may be running out of room here. So I'm going to have to try to maybe write a little bit smaller. Let's kind of squish it in there. Okay, one sign is a plus. The other sign is a minus. Okay, the square root of 25, 5 and a 5. Square root of a squared, 2 divided by 2 is a to the 1, or a to the 1st, or just a. B to the 10th, 10 divided by 2 is 5. So I've got b to the 5th, and I am going to run out of room here, and I apologize. I'm going to have to squeeze in my last 2. C to the 16th, 16 divided by 2 is 8. So that's c to the 8th in each one of these. So let me rewrite this whole entire thing a little bit neater. We have 6x to the 4th, y cubed, z squared, plus 5a b to the 5th, c to the 8th. And then the other factor would be 6x to the 4th, y cubed, z squared, minus 5a b to the 5th, c to the 8th. So again, when you're dealing with your variables, if your powers are even, all you have to do is cut them in half or divide them in half to find the perfect square. So I could say x to the 100th is a perfect square, and 100 divided by 2 is 50. And the reason for that is because if I say x to the 50 times x to the 50, when you multiply like bases here, you add your exponents, which would give me, whoops, yikes, x to the 100. Okay? So that's what this whole variable thing is based upon, is that if you multiply x to the 4th, if you multiply this x to the 4th by that x to the 4th times x to the 4th is going to be x to the 8th. Because again, when you're multiplying like bases, you're multiplying them there, you add your exponents together. So that's how all of this works. So that was another type of a difference of perfect squares. Looking at the variables, if they've got even powers, divide them by 2. And again, all you're doing is taking each square root or each perfect square and putting it in each set of parentheses in the same order, one with a plus sign, one with a minus sign. Other than that, they will look identical. In other words, this thing here is identical to what's in there, except one plus sign and one minus sign. Okay, so that's the difference of perfect squares. Those are your 3 patterns that we learned today. The difference of perfect squares and how to factor the perfect square trinomials. I do want to do one more example. There's a perfect square trinomial. This one is in the example. 12x squared minus 36x plus 27. Okay, well, 12 is not a perfect square. 27 is not a perfect square, but we always should start by looking to factor out the greatest common factor. So what we can do here, 3 is common to all of these terms. So if we factor a 3 out of a 12, we get a 4. Because 12 divided by 3 is 4, minus 36 divided by 3 is 12. Okay. And 27 divided by 3 is 9. So now we're going to check the rule for the perfect square trinomial. 4 is a perfect square, x squared is a perfect square, and 9 is a perfect square. Remember, you're only looking at the first and the last terms in order to determine whether or not that pattern might work. So what we also need to realize is that sign is a plus. So both the signs in my set of parentheses will be the same, but this time they'll both be negative. So I'm going to put 2 minuses there. Now bring down your 3. Always bring down your 3. So I'm going to take the square root of 4, which is 2, the square root of 9, which is 3, and if I multiply those together, I get a 6. Well, if I double 6 and I get the opposite of that's called my linear term, the opposite of my x term, then I know that the pattern will work for factoring a perfect square trinomial. The square root of 4 is 2, so I'll put 1 in each first position. The square root of x squared is x, and the square root of 9 is 3. Okay? So we could say 3 times 2x minus 3 quantity squared. Because again, these 2 sets of parentheses are identical, and this time even the signs are the same. Okay? So there you have all of your patterns, perfect square trinomials, and the difference of perfect squares. Okay, hopefully this helps.